that is partitioned into the constants, the inputs and outputs, and the private data for a ZK circuit. Over some of these, we define a bunch of operands as XOR accumulations of bit-shifted words. And then we can define these operand columns for the AND constraints and the mul constraints, and row by row check these constraints. So there's two primitive constraint types. The operands are made up of bit shifts applied to constants. We have logical left, logical right, arithmetic right, and XOR accumulations of those. And so, in the combination of all these tools lets us express XOR bit shifts and mul. So, how am I doing on time? Cool. So the first problem we have is embedding overhead in commitments, which is, can we commit one-bit values very efficiently? And with elliptic curve schemes, it was sort of yes with caveats. That was that table earlier that showed that the throughput dropped, but not by like 100x. With Fry commitments, we can't go below 32 bits because the field needs to be FFT friendly. But with Binius, yes, we developed this polynomial commitment scheme in this cited paper that allows packing during commitment, meaning instead of committing the bits individually, we're just going to squash all our bits into big field elements and commit those, and then use a sum check-based reduction to open our bit polynomial at the desired point by reduction to an evaluation of the packed committed protocol. And so you just think about it as the polynomial commitment scheme maximizes the information density of the committed data. So how do we even just commit big field elements? In this paper, we kind of combine tools from the Fry protocol, the Fry proximity test, the basefold multilinear PCS that uses Fry. And in our paper, we show how to adapt this for binary fields using the additive FFT from Lin Chung Han in 2014. And all of this works very nicely once we worked out the math. So how do we commit without embedding overhead? As I said, the traditional way to commit F2 elements would just be to embed them into a 128-bit field, which means padding them with a bunch of zeros, and then you need to hash more data and FFT more data. All we do is take these bits, squash them into a field element, kind of like concatenated codes, and we're going to use ring switching to make this into a polynomial commitment scheme. So ring switching's too complicated to go through all of the details in this talk, but the way it works is it's a sum check-based reduction over, fundamentally over something that's not a field but is a tensor product of fields. So we sort of think about our packing axis as one axis and our challenge axis as another axis, and do some clever things. And basically the result is it's a sum check-based reduction that reduces an evaluation claim of the one-bit polynomial to an evaluation claim on a sort of densely packed polynomial. And here's the performance numbers I ran on my laptop comparing commitments for one-bit wires in our system versus Plonky 3. So it's something like 100 times faster. I mean, and that's not shocking because we're taking something that, instead of having one per 32 bits, it's, 32 times more efficient or so. We use, their proof sizes are large because they don't properly implement round skipping in Fry, but our proof sizes are good because we implement that. OK, so that was problem number one. We figured that out a while ago. And then we got stuck on the AND constraints. OK, well, what's the problem with checking AND constraints? It's that in the sum check protocol, the first round's very efficient because we need to compute this sum over one-bit values. And then you get a 128-bit challenge, and your work just blows up. So now you're kind of stuck in the land of doing 128-bit operations. So we combine a bunch of different ideas to essentially maximize the amount of work we can do in that first round. And that first round is special because there's no challenge introduced yet. And so we sort of start from a technique in the Gruen 24 paper, which is improvements to the zero-check protocol, and then add a couple other ideas. So if we want to do small FFTs over 64 one-bit values, we can pre-compute tables for all those instead of actually computing them every time. We use this constraint packing idea, which lets us do a certain number of rounds with small, efficient, deterministic challenges, which are basis elements of our extension field. And what this basically lets us do is we're going to do a lot of work in the first round. It's going to reduce the amount of work that we need to do in the second round by 64x. And most of the operations we do in the first round is over GF2 to the 8, which has special hardware acceleration instructions on modern processors. Our next problem is integer multiplication. So emulating integer multiplication with just bits is possible but expensive. So we added a special cryptographic accelerator for this using the GKR protocol. And the idea is we're checking non-deterministic multiplication results instead of computing multiplications, and we're going to do this in the exponent of our multiplicative group. So if our field is GF2 to the 128, our order is that -1, which is basically big enough to check these results in the exponent. So we need a special GKR protocol for exponentiation using basically square and multiply, which is kind of this GKR circuit on the right. There's a few other clever things we do with for Binius reductions and so on. And our field sort of has just one too few elements, but we have an extra constraint that just checks this edge case. So this works really nicely. And the fourth thing is, again, we're comparing what Binius 64 does to a sort of naive Spartan over GF2. We're just going to reduce the amount of wiring information by exploiting bitwise parallelism. And this basically means that if we define our circuit over 64-bit words and say that every 64-bit operation is just going to do a lot more stuff than a 1-bit operation, we can just reduce the amount of wiring information, just the wiring cost. So that's why we chose this model. But we still need to do bit permutations. But the observation is modern CPUs get away just fine without arbitrary bit permutations. We just have bit shifts. And between bit shifts and masking, we can express most of the things we care to express. The way we handle bit shifts is to have this special shift reduction over the 1-bit values happening sort of at the same time as the wiring check. What basically enables this is the fact that we're mathematically treating everything as 1-bit polynomials the whole time. OK, so performance results. We are getting really good performance results on CPU from what we've benchmarked. We are beating STU and Plonky 3, which are leading SNARK implementations for hashing throughput. And this is our single-threaded throughput on various AWS cloud instances using Intel and ARM machines. And the results get better with multi-threaded performance. So Ketchak and Blake 2B are the fastest because they are naturally defined for 64-bit words. All of our 32-bit hashers are, for the moment, a little worse because we need to do masking, but we have ways of fixing that. And so what is our roadmap? As I said, we intend to add zero knowledge. That's the top priority. That's what we're working on. The protocol is also not succinct yet, but there's a transformation in Spartan to basically the thing that's not succinct is sort of evaluating the sparse matrices or the circuit. So we need to implement that. Then we're working on recursion, field native hash functions for 128-bit fields, and faster 32-bit operations to make SHA-256 go faster. So if you want to follow our progress, this is the Binius XYZ docs website, which has the full description of the protocol and all the tools and a mathematical explanation. We're on Twitter. We're on the internet. Thank you very much.